G'day everybody, this is part 3, the final part in the topic of the normal distribution. In our lesson today we're going to talk about what we mean by the standard normal distribution. How do we use the standard normal distribution? And at the end of the lesson we'll look at a particular example. How can we find the standard deviation of a normally distributed variable? So throughout this topic we've been talking about the normal distribution or things that we could model with the normal distribution. I've got 3 examples there. Let's say we're talking about the weight of a loaf of bread. It would have a certain mean, a standard deviation. We've talked about the speed of a cricket ball. It could be something like the time it takes to walk to school. Again, there would be some average value or mean, and then the time could take longer or slower, and there would be a standard deviation associated with that. So many continuous variables can be modelled with this distribution. I haven't mentioned this before, but here's the formula, or sorry, not the formula, the function that could be used to describe each of these curves. It looks a little bit more complicated than it really is. We've got the standard deviation used in that formula. We've got the mean of that distribution used in the function, and there's our value x. It's a nice little formula that sort of incorporates Euler's number and pi. It's not actually a function that you'll need to use or remember, and this is primarily because we have a CAS calculator that has all of the information we need to do with this function and the areas below the curve, which we've been using for probability. The main point is that they really are all the same curve but on different scales. And each curve could be translated and dilated. It would produce exactly the same curve. And that's the curve that we're going to talk about in this lesson. So it's called the standard normal distribution. And when we're talking about this normal distribution, we're referring to a distribution that has a mean of 0. And you can see that in the sketch, got 0 in the middle, our positive values to the right and negative values to the left. It has a standard deviation of exactly 1. And you'll also notice that when we're referring to this particular normal distribution, the standard one, we use the variable z all of the time. And whenever anyone uses z, we can assume that they're referring to the standard normal distribution, which is this normally distributed variable. It has a mean of 0 and a variance and a standard deviation, which is exactly 1. And you'll notice in the sketch, my horizontal axis has also been labelled with z. So let's look at how a distributed variable like x compares to z. You can see here we're talking about the speed of our cricket ball again, a variable with a mean of 150, a variance of 4, standard deviation of 2. I've labelled this axis x, and this is our standard normal distribution parallel to that, which I've labelled z. We're going to look at the particular value of x, 155 kilometres per hour. Now 155 is exactly 5 units above the mean. That's the distance between the mean and that value. And we're going to take into account that this variable has a scale or a standard deviation which is exactly 2. If we take that distance of 5 and divide it by that scale of 2, we get 2.5. And to put this in other words, what we've just found out is that 155 is exactly 2.5 standard deviations above its mean. That value of 2.5 is exactly what we mean by z. So to put this in a nutshell, where x is a normally distributed random variable, something like the speed of a cricket ball, Z is also a normally distributed random variable that represents a number of standard deviations above the mean. So this diagram just clarifies what we've done here. We've taken a value of x, we've subtracted the mean of that distribution, which is really its distance above or below the mean, and we've divided it by that standard deviation, which is really the scale of that graph. And it's that value that we call z, which is represented on the axis here with the standard normal distribution. In one single formula, it looks like this. This is a simple but really important formula that we're going to use. In a way, it's also reflective of the idea that with all those other normal distributions, we are translating them and scaling them or dilating them to produce the same standard normal distribution. When we're using this formula, often we're trying to solve something like the mean or the standard deviation. So we've got the formula up here. Often we know x. We can find out what z is using a calculator. We might know the mean and we're trying to solve the standard deviation, or even vice versa. There are occasions where you might need to use the formula twice with different information. You might actually be looking to solve the mean and the standard deviation with simultaneous equations. You'll notice here I've also represented the two sketches, one for x and one for z. They're parallel. I really like to sketch both curves when I'm solving problems using the standard normal distribution. I strongly encourage you to do that while you're getting used to solving problems as well. So we're going to use this problem as an example of how we use that formula and the standard normal distribution. So in our problem, we've got patrons that use a gym. We're going to assume that that's a normally distributed variable, the amount of time that they spend at the gym. The mean length of time is 45 minutes. That could be quite easy to calculate just from data recording how long patrons spend at the gym. We're going to add in some information that we know. 25% of patrons stay less than 35 minutes. And so this is enough information for us to be able to work out what the standard deviation of this distribution is. So I've defined the variable x. It's normally distributed. It's got a mean of 45. There's an unknown variance or standard deviation. Let's have a look at a sketch. So there's our mean. There's the information in the question. The probability that a patron stays less than 35 minutes is 0.25. We're trying to solve the standard deviation of this variable x. And so representing the same information but using the standard normal distribution, where we know the standard deviation and we know the mean, we've got this value of 0.25 and there's some associated value of z, which is really going to represent how many standard deviations 35 is away from 45. So let's just think about where we're going with this problem. Here's our formula. We know x, that's 35 minutes. We know the mean, that's 45 minutes. We're trying to solve the standard deviation of this distribution, and we need to know the z value. Sometimes we call it the z score when x is equal to 35. So that's where our calculator comes in. We're going to use the inverse normal function that we used in our last lesson. Using this sketch down here, we've got an area from negative infinity up to a certain value. That's what we're trying to calculate, is 0.25. Because it's the standard normal distribution, its mean is 0, its standard deviation is 1. Now you can see why the calculator has these already put in as default values. When we click OK, we get the output, which I've rounded off to 4 decimal places. So Z is equal to negative 0.6745. So I've expressed that in an equation up here. The probability that X is less than 45 is equal to the probability that Z is less than negative 0.6745. In other words, actually I've made a mistake there, I'm just going to fix that up in real time. The probability that X is less than 35, is the probability that Z is less than negative 0.6745. Remember that another way of saying this is that 35 is roughly negative 0.67 standard deviations away from the mean, negative because it's below the mean. So now we can put everything into that formula. We've got our value for Z, which is negative 0.6745. We've got our value of X and our value for the mean of that distribution. We can now solve the standard deviation of this distribution, which turns out to be approximately 14.8 minutes. So now we know that we've got a normal distribution that has a mean of 45 and a standard deviation of 14.8. And so once you know those two things, you've defined that normal distribution. You could work out any other probabilities that you wanted to that were associated with that distribution. So that concludes the lesson. Let's just do a quick recap. We've talked about what we mean by the standard normal distribution, how all other normally distributed variables can be scaled back to this one distribution that has a mean of 0, standard deviation of 1. We've seen how we use the standard normal distribution, in particular that simple formula that we use. And our example that we finished the lesson with was to find the standard deviation when given other information about a normally distributed variable. Please write down any questions you have from this lesson, and remember to complete the Google form to log your attendance, check your understanding. Thanks very much.